let let G be a non-empty set and star is a function from G cross G to G. This is a function from G cross G to G, be a function. Sometimes we call star as a binary operation. Reason is very clear that because we are taking pair of elements here, so we take words binary. So binary operation, and we are taking the same elements from the same set, and the resulting elements is also from the same set. So we say that this is a special kind of function which takes any two element of G into another any element of G. So that's why we call this is a binary operation on G. It's a binary operation on G. It straightforward implies that for any AB belongs to G implies that A star B belongs to G, because star is a function, and if you take any two elements here AB, then there must be a unique element G, and that unique element is denoted by A star B. So this property is known as closure property. Closure property. Sometimes this is this is known as first property of a group, but we will write the first property as associative property. Associative property means for any three elements A, B, C belongs to G. So there is a question, we can operate two element at a time. So first we operate A with B and then with C. It is same thing is first we operate B with C and then operate with A, and this property is known as associative property. Next property is existence of inverse of identity element in G. So for any A belongs to G, there must exist an element E belongs to G such that A star E equal A equal E star A, means E is a special element of G that can be operated with any element of A will give A. So no effect of E with operation with A under that operation appear. So this special element E is known as the identity element of the group G. So E is called the identity element in G. Third is existence of inverse element. Existence of inverse for any, we define in such a way, for any A belongs to G, there exists B belongs to G such that A star B is E and B star A equal A. B star A is also E. So this is a special condition when every element can be operated with some element of G and resulting element will be the identity element. So this is the third property. So if G is a non-empty set together with a binary operation satisfies associativity, existence of identity element and existence of inverse, then this pair is called group. This pair is called a group, and sometimes we include the definition in the definition of group closure property. So sometimes we say that G star or simply G is a group if it satisfies the following axioms. First is closure property, second is associativity property, third is existence of identity element in G, and fourth is existence of inverse of each element in G. So in addition to this, if A star B equal B star A for all AB belongs to G, then G is called a commutative group. And this property is known as commutative property. So a group with these five property, a non-empty set together with the binary operation, when these five property is known as abelian group. Now I give an example of a group. Let this denote the set of integer. And plus denote the binary operation, the usual addition of numbers. Then this pair forms a commutative group. A commutative group is also known as abelian group due to the name of the mathematician Abel. So a commutative group is also known as abelian group. So now we can see how this set of integer with this binary operation addition forms an abelian group. First of all, for any two integers n and m, n plus m is also an integer. So it is readily verified that sum of two integer is again an integer. So this is closure property is defined here. closure property is defined here. One can verify, one can see these conditions for positive integer easily by writing n by 1 plus 1 plus 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 1. This is n times if n is a positive integer. And if n is a negative integer, then n can be written as minus 1 plus minus 1 plus plus minus 1, and this is mod of n times. So this can be readily verified that the sum of two integer is again an integer. So this operation is a binary operation on Z. So Z is closed under addition. This property sometimes is known as closure property. So closed under addition of numbers. Okay. Now we take next property, associativity. So we have learned that second property, or you can say first property, for any n, m, k integers, we know that if you take n plus m, this is an integer, and if you take k with it after considering m plus n, this is integer, then this is also an integer, and this gives the same integer. So this is true. We have learned in previous classes, in lower classes. Second is there exists 0 in integers such that n plus 0 is n equal to 0 plus n for all integer n. And third is for any integer, positive or negative, there exists minus n is also an integer such that n plus minus n is 0 and minus n plus n is 0. And you can see fourth property, n plus m equal m plus n for all nm belongs to integer. So this is quite easy. One can think about integers is an abelian group under addition, usual addition. Next we will see that the set of integer is not a group under usual multiplication. Of numbers. That is, we can see that if you take two integer, then their product is also an integer. Okay, this can be seen. So there is a closure property. Associativity is also there. N into m k is n m k for all n m k belongs to integer, and there is existence of identity element is also there. One belongs to integer such that 1, this is n for all. But one property it doesn't meet of group, that is existence of inverse. For example, if 2 belongs to integer, then we can think about an element n such that 2 into n equal 1, where n is integer. So we see that there exists no such n in Z. However, n equal to 1 by 2 in Q, the set of rational number, okay, but not in Z. So therefore this is not a group. Such type of structure are known as monoid. A monoid means a structure having closure property, associativity and existence of identity. And a structure that has only two property, first and second, means a closure property and associativity, is known as a semi group. So in this video we have learned about group, its definition and one example, the set of integer. That is very important example. Now we can think of we can consider more examples here. We can consider more example here, if we take example let G be a set consisting with matrix. A is a matrix containing Aij element, where Aij is integer for 1 less than I less than m, j less than n. In fact, the collection of G is a collection of all m cross n matrices over integers. So if we take binary operation, the addition of matrices, okay, say this is plus, okay, addition of, so we can see that this set G forms an abelian group. So one may prove that G is a group, is a commutative under addition of matrices, So I think it can be verified easily that if we take two matrices A and B belongs to G, then they will be of order m cross n, and their sum will also of order m cross n. And since entries Aij are integers and entries in this Bij are integers, so entries of this Aij plus Bij also integers. So this can be seen easily that this is a closed under addition. Associativity we have seen many times in previous classes. matrix addition is associative for all A, B, C belongs to G. And we know that zero element, zero matrix, the zero matrix is in G such that A plus 0 equal A, 0 plus A. So this proves the existence of identity element. And for any A belongs to G, that implies A is Aij m cross n order matrix. Now we can set a matrix B with entry Bij, where Bij equal minus Aij. Then one can see that A plus B is Aij plus Bij is Aij plus minus Aij, and finally you get that Aij minus Aij is 0. So all entries are 0. Similarly B plus A is 0. So this proves the existence of inverse of every matrices, additive inverse. And last is A plus B is equal to B plus A. The matrix addition is commutative, so we can see that G is an abelian group or a commutative group. There can be more example that can prove. We can see about this the same group G. Let G, we can say this is, if we take it here, this G, now this is, we now consider G is a matrix. A is a matrix Aij, and Aij belongs to Q, the set of rational number, and 1 less than Ij less than n be the set, the collection of all square elements, square matrices over Q, the set of rational number. So if we define a binary operation, the product of two matrices, then this is quite a binary operation. Then this product, the product of two matrices. Okay. So G star is an algebraic structure. Algebraic structure, we mean that a non-empty set together with at least one binary operation. So we can say that it is closed, G is closed under the multiplication, under the product of matrices. Second is associativity is there, associative. And third is there exist identity matrices belongs to G, identity matrix. But fourth property cannot be taken granted. If A belongs to G, then there may or may not exist B such that A cross B equal identity matrix. So it means that G is not a group under the multiplication, under the product of matrices, product of two matrices. So this is an example when the collection of square matrices is not a group. But if we consider these collection as non-singular matrices, so that can be a group. So we have studied some example. Now we learn a property of this identity element and inverse element of a group. So this is a lemma, you can say, a result. In a group G, the identity element is unique. Identity element is unique. So proof is very simple. If we take two identity element, let E1 and E2 belongs to G, be two identity elements. So from the definition, if we take E1 as an identity, as the identity, and E2 is any arbitrary element, we implies E1 E2 equal E2 and E2 E1, because E1 is identity element, so if we operate with E2, the resulting element will be E2. In similar, if E2 as the identity element, then you will get E2 E1 is E1 and E1 E2. It means that E2 is identity element and E1 is any element, so resulting element will be E1. So that implies E1 is E1 E2. From this, E1 is E1 E2, and now from this, E1 E2 is E2. So that implies these two elements are same. Okay. In next result, we will prove that inverse of every element is. So in a group G, the inverse of each element is unique in G. So let A belongs to G be any element, and B and C act as its inverse. So by definition, AB equal E equal BA and AC equal E equal to CA. So from this we can take that implies B can be taken as BE. Okay. Now BE can be taken as, from here, BE can be taken as, this is AC. Okay. E can be replaced by AC here. Okay. So if we take associative property, then it is this. Now BA can be taken as identity here. So this is E, C, and this is C. So this proves the existence of, this proves the uniqueness of of inverse of each element. Thanks for listening me. Please let me know if there is some confusion or some query in comment section. Thank you.